Good afternoon, everybody. Right, what I'm going to follow Peter with here is to sort of come back to some of the environmental issues around shale gas, and particularly looking at the groundwater aspects and the wider environmental aspects. So looking at groundwater well integrity and the use of water as well. Sensitivity, right? The back one. Oh. Again, there we go. So what I'd like to do to start with is really just to talk a little bit about groundwater to set the scene really, so that they can then go on to talk really about some of the environmental issues associated with shale gas, or potential environmental issues anyway, looking at the water requirements and demands of the industrial activity that will take place, look at some of the potential pollutant sources associated with shale gas, and then think about the pathways which may be implicated in terms of movement of those pollutants if they happen to the environment, and then think about some of the treatment processes, really just touching on the wastewater treatment process of the industrial waste that we've produced from the activity. Now, as Mike said earlier this morning, there really is a growing amount of information available, particularly considering the environmental aspects, and a lot of this is anecdotal information, a lot of misinformation as well, so it's very hard to pick out of that what is real information, and the amount of peer-reviewed science as well is very limited. So I've tried to draw on some examples throughout the talk in terms of what we know and what are peer-reviewed publications, and also, if you like, publications that have been validated and verified. And much of this relates to other countries and not the UK, obviously, because we are at the very early stages of shale gas exploitation. Now, we've seen the map on the left already, looking at the potential shale gas deposits and their distribution across the country. I wish I'd had Mike's map as well, because on his map he also showed the subcrop area. So, and particularly here where we have the Jurassic clays. Now, one of the things about this map is it really shows the surface outcrop of the shales. It doesn't show the full distribution of the subsurface, whereas Mike's plot showed, particularly here, an example of where the Jurassic clays dip and extend below in the subsurface. On the right, I have a map showing the distribution of the main aquifers in England and Wales. We have the chalk in green, the Permo-Triassic sandstone, and the various aquifers distributed around England and Wales. And these are our principal drinking water aquifers. Now, in addition to that, the white areas doesn't mean there isn't groundwater. There is also groundwater in those areas, and in many areas there are minor aquifers or secondary aquifers there that are now referred to, or areas of very shallow groundwater which are not suitable for supply of drinking water, for public supply. They may support smaller private supplies, but also groundwater is very important in terms of supplying base flow to our rivers and to our wetlands. So we have to consider not just groundwater, but the groundwater within the context of the whole water environment. So you can see quite clearly that looking at England and Wales, the juxtaposition of aquifers and shale gas is something, or shale deposits, is something that needs to be considered very carefully in terms of planning and managing this activity. Not dissimilar to many of the other activities that take place, which involve exploration or disposal of materials in the subsurface. As I said, I'll just set some of the context really in terms of groundwater protection. We rely very heavily on groundwater in the UK. It's a very important drinking water source, and I mean, as you're all aware, we're currently in drought still in some parts of the country. The drought was considerably more extreme when we had dry weather, but obviously it's, as they say, the wettest drought on record now. And where we've had drought in this recent year, it's actually been principally as a result of depressed groundwater levels and a shortage of groundwater in areas. So we rely on groundwater, as I say. 35% of our drinking water comes from groundwater across the United Kingdom, and in some areas we're even more dependent on that, particularly in the southeast, for example, where our chalk aquifers are our dominant and principal source of drinking water. 80% of drinking water comes from groundwater. And we have around about 2,000 public water supplies distributed across England and Wales, and in addition to that, tens of thousands of private supplies as well. And as I've said, groundwater is important to supporting surface water flows and the ecosystems dependent on that. And the Environment Agency has set out to ensure that we put in place measures to protect groundwater, and I know Tony will talk a little bit more about that, but I wanted to say that, particularly as a hydrogeologist, we take groundwater protection very seriously in the UK. And we have a range of tools and approaches to protecting groundwater. We apply a risk-based approach to groundwater, and that addresses and takes into account the range of activities which put pressures on groundwater. And we also have European obligations as well as UK obligations in terms of protecting groundwater, and there are some very clearly defined environmental objectives associated with that. And I guess Tony will talk about the Water Framework Directive and Groundwater Directives, which are particularly pertinent to groundwater. And those objectives associated with groundwater relate to preventing and limiting inputs of pollutants, ensuring we achieve good status, so that means we have enough water to meet the requirements of the human demand as well as the environment, and also for the surface waters and protecting wetlands, and we also can meet this sort of diverse range of demands on our water environment. And to do that, we have a range of tools. We have regulatory instruments and regulations, but we also have supporting tools, risk assessment methodologies and models protecting groundwater, supporting tools in the ways of sort of groundwater vulnerability maps, source protection zone defined to protect public water supplies, and also we have codes of practice and guidance to ensure groundwater is protected, both proactively and reactively as well. So we aim to protect groundwater, but deal with problems as and when they arise to remediate as quickly as possible. And another aspect of that groundwater protection is ensuring that we have adequate monitoring to ensure that the measures are appropriate, and also that we take the actions that we need to should groundwater become impacted by over-demand, by over-abstraction, or by impacts from pollutants. And so we'll talk about monitoring a little bit later. So that really sets the context of the talk and the need to protect groundwater. Again, I'm only pressing it once, honest. Okay, so looking now firstly at the water consumption side of shale gas production. Again, there is a lot of information that is in the public domain with respect to the amount of water that is required for shale gas. And we've heard already the processes involved of drilling the well and then subsequently undertaking the fracking activity. Now, really the use of water is for quite a short period of time on any individual well, but as you scale up and have increased numbers of wells, then that demand for water increases and continues over a longer period of time. I've identified there the range of water, a range of volumes of water that which is needed for drilling and also for fracking. Less is required for drilling than for fracking, and the differences really and the variations reflect very much the complexity of the drilling operation, the nature of the geological conditions into which the well is being sunk, the depth of the well, and the distance in the horizontal plane in terms of the directional drilling, and also the number of fracking stages. So hence there is a very broad range of numbers in the literature, but increasingly there is more accurate reporting of the amount of water that is being used by the industry, particularly in the United States, as they are becoming more aware of the need to report the facts. So again, you can see, and these are very large, appear to be very large numbers, just to give you an idea in terms of how big those are. If we look at the top number there, the drilling, the largest, the number for drilling, the 4,000 cubic meters, is equivalent to about 2 Olympic swimming pools. And for fracking, the 23,000, about 11 Olympic swimming pools. So that gives you an idea, and that's for an individual well. But obviously, that's required for a single well. Those give numbers for a single well. If we think now about scaling that up in terms of what would be needed for maintaining production of gas, I've taken the numbers here from the Tyndall report, which is a good basis just really to make some estimates, and that was the Tyndall report was mentioned earlier. And considering that this report considers how much water we would need to maintain 10% of the UK gas demand over a 20-year period. And that's equivalent to an annual demand of 9 billion cubic meters of gas. So in order to do that over a 20-year period, we will need between 25 and 33 million cubic meters of water over the lifetime of that period, over 20 years. If we divide that effectively by 20 to get an annual water demand, that ranges between 1.2 to 1.6 million cubic metres, which seems a large amount of water. But then when we look at the total licensed annual water abstraction for England and Wales, and that's just that's non-tidal, so that's sort of inland freshwater abstraction, that's equivalent, that figure is 12.2 thousand million cubic metres. And so what we're looking at here is actually, in the grand scheme of things, shale gas requiring a relatively small amount of water compared to other types of abstraction, less than 1/10 of 1%, in fact, of the annual abstraction of fresh water for the range of uses that we use it, and that includes drinking water abstraction and energy production as well. But that's really looking at it in the grand scheme of things. What is important then is to look very much in terms of, although it's only a small amount, how does this fit into water availability, water resource availability across the UK? Because shale gas, if it takes place, will be localised, and therefore we'll need to look at the availability of water in specific areas where that activity takes place. And the map on the left is from the Environment Agency's Water Resource Strategy from 2009, and the agency manages the water environment, as I've said already, and it manages the abstraction of water from both surface water and groundwater in an integrated way through the catchment abstraction management strategy process. And the map shows those areas based on their assessment where water is available for licensing, where it's over-abstracted or where it's fully licensed. And the red areas show areas where a potential stress and where there is limited resource available for future abstraction, and where the agency will be looking to manage very sensitively the demands on the water environment. That doesn't mean necessarily that water isn't available, but the management has to take into account all of the demands on the water and also the needs of the environment. And just on the right, because the map on the left is looking at both groundwater and surface water combined, on the right I have a map there showing the outcomes of the assessment undertaken for the European Water Framework Directive, just focusing on groundwater, showing the groundwater bodies that are failing to achieve the good status requirements for quantitative status. So that is failing to achieve their environmental objectives, and that is principally because of those areas being the abstraction exceeding the long-term available recharge in the aquifer, and therefore putting pressure on the environment. So it really just puts that in context in terms of water demand. For shale gas, the amount of water is relatively small compared to other things, but we have to see that in the context of the wider water management system. Now moving on to some of the contamination concerns. And again, we've heard about these throughout the day, particularly the contaminants, and I'll go through some of the contaminants in a little bit more detail and then look at the potential routes to groundwater. So I'll talk about methane as being the main component of the shale gas that is being produced, the fracking chemicals, what is involved in that, and also looking at the flowback fluids and the produced water, which is what comes out of the well following the fracking procedure. And then look at some of the potential routes to groundwater and other receptors for those, principally looking at the geological pathway, which as a result of fracking, although I don't really need to say a lot more about that because that has already been talked about in some length, looking at the potential for well casing failure as a pathway, and then looking at activities on the surface, which again may be sources of release of contaminants. So firstly, looking at the composition of shale gas, I don't think anybody's shown slide or the composition today, so it's worth having a look at that. Clearly the main component of shale gas and the purpose for undertaking the activities to extract the natural gas, the methane. And again, the content of shale gas ranges in terms of methane between 70 and 90%, again depending on the geological formation within which the activity is taking place. In addition to the methane, there are also smaller amounts of other light hydrocarbons, ethane, propane, butane and so on, and again the amount will vary depending on the geological conditions in the formation. There are also small amounts of carbon dioxide, oxygen, nitrogen and hydrogen sulfide, differing amounts, and also rare gases which are produced in the subsurface, and also radon as well, because we've already heard a little bit about the fact that there are issues around, or some of the shales can contain uranium or naturally occurring radioactive materials, and radon gas can also be released during the hydraulic fracking process and the shale gas production process. So just to give you a context, that clearly we're extracting methane as an energy source, and therefore hydrocarbons such as methane are explosive, and they're explosive when they reach between 5 and 10% of in a confined space, and that's when they become explosive. And radon is obviously a gas which is radioactive and also carcinogenic, and is cause for concern if uncontrolled. Radon has a very short half-life of about 3.8 days, so very rapidly it will decay away. So generally, unless we have exposure early on, it doesn't pose a problem, because the length of time between extraction at the surface and, for example, gas being put into supply, there is a longer lag time than that. So the radon is not generally considered to be an issue, although something that should be aware of. Now coming on to fracking fluids, and again, as we heard earlier, the principal components of the fracking fluid is water and the proppant sand, and in addition to that there is a small amount of chemicals added to enable the fracking fluid, or the sand and the water, to reach the formation depth and to effectively ensure the fracking process is efficient and can be sustained, and that the operation is effectively undertaken. And the range of chemicals that are introduced within the fracking fluid are quite a small percentage of the total. I've got a range there of 0.1 to 2% is the amount of chemical additives in there. But generally speaking, there seems to be, from a study of the literature, a reduction in the amount of chemicals that are now added. There has been difficult here because over a period of time there's been quite a lot of secrecy about the constituents of the fracking fluid, particularly the chemical mixture, but now there is greater openness in the States. I think people recognition of the need to ensure that there is openness, and there is now a system of voluntary revealing of the composition of the fracking fluid. In the UK, it would be very different because of the regulations that are in place. There would be a requirement to disclose and seek prior approval for the use of chemicals used in fracking fluid. I'm sure Tony will talk about that later. But just to give you an idea, the range of chemicals that are in the fluid can be seen on the left. In addition to the water and sand, then there are you can see here, sort of a range of chemicals added. Acid for looking at surfactants, pesticides, to ensure that there is no range of compounds are added, but in fact there is a move to try and look at, if you like, simplifying the number of chemicals used to reduce that down further. But if we look, as we have at BGS, at the range of chemicals reported in the literature, some of the chemicals would not be allowed to be used in Europe because they are considered to be hazardous substances. But as I say, this really is reflecting what's happening in the state where there are fewer regulations. Now, in terms of the flowback and produced water, once the fracking fluid is injected and the pressure is released, we then get the flowback water, which is effectively reflects the chemical, the composition of the fracking fluid, but also it's modified by the return to the surface of some of the residual materials from the drilling operations, and also materials from the formation itself into which the fracking has taken place. And over time, the composition will shift as we get the flowback water, which reflects very much what has been injected, reduces, and that is replaced increasingly by a large proportion of the formation water, which reflects what is in the subsurface in that fracking area. And the produced water effectively can include a range of additional substances, which include metals, which again are withdrawn or reflect the composition within the geological formations, and those can include zinc, chromium, and nickel and other heavy metals, also arsenic, sodium, calcium, magnesium chloride, which really reflect the formation waters again. And as I've always said, there is potential for naturally occurring radioactive material to be returned to the surface as well. In particulate form, this can be in uranium or radium. As I said as well, the gas will return radon as well. Now, in terms of handling of that flowback water when it comes to the surface, there are issues around that water that clearly needs to be disposed of, the water needs to be disposed of, and there are, for small amounts of flow back and produced water, industrial wastewater treatment plants are quite capable of handling the liquids and the fluids that come to the surface. And again, I'm sure Tony will talk later about the environmental regulations around that. But obviously, as there are larger volumes, then more specialist processing may be needed to handle the volumes needed. And from the States now, experience from the States is showing that increasingly there are treatment processes being developed for handling the larger volumes which are being produced there. And that involves the separation of the solid material, the processing of the liquid to enhance flocculation and precipitation of materials in suspension, and then treating the liquids that remain by processes such as distillation, industrial distillation, effectively to ensure that there is further removal of the contaminants to produce a wastewater which can be released through a wastewater treatment plant or directly discharged to the environment if it meets the required standards. There is a residual available that does require further disposal, but the idea is to try and reduce the amount that needs disposal ultimately. And also the treatment is being optimized to look at producing a material that can be used or reused in the fracking process. And again, I think this is something that needs to be considered further, and also the need thereby doing is to make sure we reduce the amount of water we use in the first place, but also effectively ensure the operation is more efficient and reduces less waste. So now coming on to methane, looking at methane, and we've already heard, I think from Mike earlier on, that there are a range of sources of methane in the environment. On the cartoon on the left just shows some of those, for those of you who are not aware. There are deep sources of methane, and clearly we know that as Mike said earlier, we extract gas conventionally. We've done that for many years. We're looking at shale gas here as an unconventional source of methane deep in the subsurface. We also use the subsurface to store gas as well, for short-term storage of gas. But we've also got sources of gas near the surface as well, and there are quite a number of sources of gas. So we have obviously landfill gas, or gas produced by through waste disposal. We have peat bogs and wetlands with high organic compound. Again, we have methane produced in those situations. So there are a wide range of methane sources in the environment, and it's fair to say, I think, that to some extent methane is ubiquitous in the environment. Now that presents a challenge, particularly where we have to look and consider source identification, and Mike said earlier on, and he gave some indications of that. And we've also had evidence of impact of methane explosions, and I've got pictures on the right here which show the impact of methane escaping to the surface and causing problems. So the first one here is in 1984 was the explosion at Abisted, which was a pumping station associated with the transfer of water between two rivers. And at that time there was a meeting being held in the pump room, in the pump house, in the valve house, and the tunnel had been empty for quite a period of time, and this has allowed the build-up of methane, which subsequently caused an explosion in the pump house. And I think there were something like 14 people were killed in that explosion, and 66 people injured. And on the top there we have another explosion in Losco in 1986, where a bungalow exploded. Now, the sources of methane in these cases were very different. And after detailed scientific investigation to the cause of the methane, the bottom explosion was caused by gas of thermogenic origin, geological source of methane. The gas at the top was due to biogenic methane caused by the migration of landfill gas. So we've had a very long history, because of these incidents, of looking at trying to differentiate between different sources of methane in the environment, not just for shale gas, but because of other environmental issues around methane in the environment. And it's been taken very, very seriously. So looking at some of the properties, and we heard about stable isotopes, and I'd like to just look at some of the properties around methane, which we can use for source identification. We've heard already that there are principally two sources of methane, biogenic and thermogenic. and we had an explanation earlier of how they were formed. Biogenic methane principally produced in the near surface as a result of the microbial alteration or microbial decay of organic material, and thermogenic origin is produced at depth of the transformation of organic material, high pressure and high temperatures at depth. As a result of the different processes of production, that means the gases can have different properties, and one of the properties we can look at is simply just looking at the composition of the methane and its associated gases. So, for example, looking at the ratios of methane, ethane, propane, butane, and so on. For biogenic gas production, mostly the gas is methane with very small amounts of the other components. But for thermogenic gas, there can be a larger amount of the ethane, propane, and butane. And so we can look at the ratios. But again, there is variation between different gas sources. Another tool that we can use is stable isotopes. Carbon has three main isotopes, 12, 13, and 14. Carbon 14 is a radioactive isotope. Carbon 12 and carbon 13 are stable, i.e. they don't decay radioactively. And we can look at the ratio of the isotopes in relation to an international standard to characterize different sources of gas. And again, as I said, a lot of work has been done on this to distinguish landfill gas from other sorts of thermogenic gas or even biogenic gas. And we can use that very effectively for differentiating the gas. We can also use and look at carbon 14. In modern biogenic gases, carbon 14 is measurable, but in very, very old thermogenic gases, the carbon 14 is effectively not measurable because of the geological timescales involved. All the carbon 14 will have decayed. So again, we have a range of tools that we can use for source identification. And the plot underneath there shows how we can look at and combine these different tools to differentiate between different sources. One of the complicating factors, however, is that some of these ratios and the isotopic ratios and the ratios of different gases can change as the gas migrates away from its source of origin. And a biogenic gas that migrates away can undergo microbial oxidation and its isotopic structure change such that it begins to resemble a gas of a different type. So when we interpret information that we get from our measurements, we have to be very aware of the changes and transformations that can take place. Now looking at methane and groundwater and thinking about how we might use some of these tools, the graphs on the left are taken from some of the literature we've already heard about there. The top one from the Osborne paper and the bottom one from the paper by Malofsky. And clearly on the left we can see a graph which shows, just to explain the graph to you, we have concentration of methane on the left axis, and at the bottom here we have distance away from the nearest gas well. And as Mike said, this paper is very controversial, and Richard and others have written rebuttals about the paper. But clearly these data show that you can see high or get high methane concentrations in groundwater, and this grey bar across here is the action level. So we're saying that concentrations up here, if measured in water, could be the source of problems with respect to if that gas builds up in a confined space. Now, what we've got is, in this situation, is clearly an issue with respect to methane. But as I've said, the interpretation of the data requires very careful and considered thought. And I think Mike said earlier that there are other possible sources within this area, and that on further investigation of this paper is clearly the case. And this plot here is from the paper, one of them that addresses the data set. And you can see we're using here, again, the stable isotope ratio plot. And this highlights the areas where we've got biogenic characteristic gases and thermogenic area. But the thermogenic gases have been subdivided, and this small circle here reflects the composition of gas from the Marcellus shale, which is the actual shale that is being exploited in this area of study, but also samples of gas from other shale formations within the geological sequence at a shallower depth have different isotopic signatures. So unless very carefully look at the range of possible sources and the pathways, then it's very easy to misunderstand and misinterpret the data. And therefore, it's very important that we look at multiple lines of investigation and evidence to make a decision. And the subsurface provides multiple sources of methane and other contaminants and pathways, both natural and engineered. So just looking at the pathways from a geological perspective, the graph on the left we've already seen, so I don't need to describe that, but that plot is from bringing together all of the available information on the Marcellus Shale and the fracture generation associated with that, and the depth of the overlying aquifers. And this plot shows that the top of the highest fracture and the aquifer is around about 1,200 metres, so quite considerable distance. This information has been collected in the States, and there's quite a lot of information, as we saw earlier, on that. What about the UK? Well, we have an enormous amount of information on the subsurface in the UK, and we're starting to bring that information together to produce 3D geological models. That's complex, but just to show you on the right there, something we're doing at the Geological Survey is bringing that information together, and we've produced a national fence diagram model. So that is a series of cross-sections across England and Wales, which do actually extend into Scotland as well. And you see quite a dense network of cross-sections, and this is shown here as work in progress. So we can look at the relative locations of shale, horizons, and overlying geology, and also the position of aquifers. And so we're working on trying to better characterise the pathways in the subsurface between potential shale plays and overlying aquifers. And that is a piece of work that's been jointly between the British Geological Survey and the Environment Agency. But as we've seen already, the extent of the induced fractures vertically is limited from experience of seeing, and the distance between receptors, between the source and potential receptors, is thousands of metres. But we do have this multi-layer complex geological sequence in between, the properties of which we do need to understand. Again, well design has been touched on again, and this does, wells that have drilled into the subsurface do present potential pathway to the subsurface if the wells are not properly constructed. There are industry standards for well design. This is not new. There are the design standards that will be used or proposed for shale gas are typical oil and gas well design standards. So the American petroleum industry has a range of standards that apply. There are British standards being under development or currently developed, and also the Health and Safety Executive will be regulating well construction. So there are industry standards, and if the industry standards are followed, then the integrity of the wells will be fine. That will take into account the selection of required materials, the completion standards with respect to casing and other materials used, and as we've heard earlier, the completion involves the installation of a series of different stages of well casing down from the surface, where we have conductor casing and surface casing, which is down to depth below the lowest level, well below the lowest level of the aquifer, and then down to intermediate casing before finally the production casing. And each of the casings are isolated from each other and from the geological media by the use of cement. And again, procedures are in place, and Peter, I think mentioned this, that the wells are tested, and there are a range of techniques that can be used for ensuring that the bonding between and seals between the casing and the borehole are proven and will meet the requirements for operation for the required period of time and beyond. And again, the various logs that can be used are the cement bond log and the variable density log, which can be run to look at the integrity of the well and guarantee the integrity of the well. That information will be used to demonstrate that the well meets the requirements that have been specified. However, having said that, I mean, that's in an ideal world, and we need to make sure that that those wells that are installed meet those requirements. But there is evidence from the States of poor design. I'd just like to give you an example of this. And this information is taken from a study which is being published currently is a draft report from the US Environment Protection Agency where they're investigating the incidence of groundwater pollution, which is believed to be attributed to the unconventional gas production. And this effectively reflects an example of poor well location, design and construction, and I'll explain why. It's a study which relates to an area called Pavilion in Wyoming, and there are something like 196 gas wells in this area, but in this case the exploitation of the gas and the fracking activities have taken place at relatively shallow depths, and in areas, and they were undertaken over a period of time during which there was very little or no regulation or inspection of well design. And we have, in this situation, sorry about that, the exploitation of the gas was as shallow as 372 metres below ground level, and that was overlying that were aquifers which were exploited to 244 metres below ground level, and the base of the aquifer was lower. And through the investigation, quite a number of issues were identified that could potentially lead or have led to the pollution of shallow drinking water abstractions. And on the left, the plot on the left effectively shows some of the gas boreholes along a cross-section through the area, and the water wells are in the pale blue, which are relatively shallow, and the production wells are the deeper wells. The colour coding reflects the testing or the integrity of the casing and the cement bonding around those, which will isolate the well from the surrounding geological formation. And if you can see that where we have the orange colour and where the bonding, the casing, was very poorly designed, so clearly very quickly could see that the integrity of the wells was not very good at all, and this was due to the poor installation and regulation and the management of the sites. And as a result of that, it has the potential for introducing pathways of the movement of contaminants from the subsurface. But on top of that as well, poor management on the surface was implicated as well for the release of contaminants, with the use of storage pits for holding the produced and flowback water, and a number of these were found to be leaking and plumes associated with that identified. So there are a number of pollution sources here, and it's quite an interesting study to look at, which shows some of the poor management issues around the process. But clearly that was looking back on what was the situation quite a while ago. But it gives a good indication of what issues we need to tackle, and we need to learn from this to ensure that we get things right in the future. And in terms of thinking about some of the baseline now, just to talk about the baseline, because we already have quite a lot of monitoring of groundwater that we undertake. The Environment Agency is principally responsible for that. But jointly with the Environment Agency, the Geological Survey has actually produced quite a comprehensive series of reports on the natural quality of groundwaters across England and Wales, and also with SEPA, the Scottish Environment Protection Agency, the natural quality baseline reports for Scotland as well. And these are all available on the web. And these really look at what the natural quality of groundwater should be without, if you like, any alteration or anthropogenic signatures imposed on that. Now, this study was not done for shale gas. It was done on the basis of ensuring we understood what the natural quality was and the potential future impacts for a range of activities that could impact groundwater quality. So we have quite an extensive amount of information on that, and the scope of these reports covers mostly inorganic chemicals within the groundwater system. It looks at the geological and hydrogeological context. It interprets the data with respect to historical and current land use and the various controls on geochemistry, because there isn't a single number that can represent groundwater quality. The concentrations of parameters varies across an aquifer related to the pathway along which the groundwater is flowing and the evolution of the chemistry in the subsurface. That is all natural processes, both with depth and with movement, with spatially and vertically as well. What we didn't have was a huge amount of information on methane in groundwater. There are a number of measurements already. So the map on the left shows the number of data that we have, or the amount of data we have for methane and groundwater, the red dots there. And these were data that have been collected as a result of a range of research projects over a number of years, not related to hydrocarbon exploration, but just as part of the process of understanding chemistry of groundwater. So although we have some measurements, we don't certainly have a good spatial distribution of monitoring. And so what we've recently undertaken at the start of this year is to enhance that database, to look to extend our monitoring to areas which are potentially likely to be explored, potentially exploited for shale gas in the future, and to undertake monitoring to build up the baseline data set. Because I think, as you've heard earlier, clearly understanding the baseline before the activity takes place is very, very important. And so the areas in green are the areas we're going to focus on and supplement the existing data set to build up that data set and make that information, some reform, publicly available. So in undertaking that a sampling program, we are principally identifying observation boreholes which are operated by the Environment Agency, and also a range of public and private water supplies to obtain water samples from. And we'll undertake an analysis of the samples for dissolved gases looking at methane, carbon dioxide, plus the general water chemistry as well, to supplement our data set on inorganic chemistry. Where we identify methane in the samples, we will repeat sample and then measure the carbon and hydrogen stable isotopes of the samples of both the methane and any dissolved carbon dioxide. And where appropriate, we'll consider looking at carbon-14 as well. And we'll also look at trace organics in the waters, as well as characterising the waters by looking at the residence time indicators. So looking at the CFCs, fluorocarbons, and SF6 as indicators to provide an idea of the age of the groundwater, so we can put and interpret the chemical information in the context of what we find. We'll also be looking at microbiological indicators as well, to see whether there is any evidence of either methane generation or methane oxidation within the water samples, particularly where we don't find high levels of methane, and again to understand the context of the results. At the same time, we're collating any other information as well as the BGS data to bring that together to produce this national baseline data set. So just to finish off and just to summarise then, I mean, I think there are a number of areas, obviously clearly we've identified, which have the potential for shale gas exploitation, which underlie some of our aquifers and our imported aquifers. The groundwater protection needs to be taken seriously, but the measures that we have are effective, and they exist already, or they exist and they are effective. Water demand, as I've shown, is for shale gas production, if we project that forward, is not a significant issue relative to other uses nationally, but there may be local availability issues, and that needs to be taken into account when looking at a developing industry, like any other industry that we'd have. Shale gas exploration produces and uses a range of chemicals, and it also mobilises chemicals in the subsurface as a result of that activity. They are potential pollutants, and the risks will need to be assessed and managed effectively, but we have the tools to do that, and the standards appear to be there to ensure that the activity can take place. And I think, based on a review of the available literature, the biggest risk, I think, from the activity is activity associated with the surface. The storage, transport, and movement of chemicals and the fracking fluids on the surface, and those are the issues. Looking at the literature and around the states, followed by lack of regulation in the states, which has led to some of the problems we see, and also the poor well design and completion, which are the principal problems that we see from the states. Thank you.
Thank you very much. I'm conscious that we are likely to run a little bit behind time leading into the next talk. So equally, I'm sure that there might be some important questions following a very meaty presentation just then. So if we have time for 2 or 3 questions, I'm happy to take those now.
Hello there, it's James Adley from Cranfield University. You mentioned extensively how you think about recycling the water used and possibly going through municipal treatment, but what methods would you use to treat the residual solid left over? Would you be able to use it for land spread or vitrification?
I'm not an expert on the wastewater side of it and the processing operations, so I don't think I can answer that one.
Second question. Okay, I think we might have to pass that question on to one of our environmental engineering colleagues. But move on to another question here, please.
Hello, John Hackett, Anglian Water. I'm very much involved with borehole construction, and I'd just like to understand, although we've got these policies of construction that are well established, whether it's time to look rather innovatively in incorporating monitoring devices that give us immediate responses to, say, like pressure relief or casing failure, where Peter was alluding to immediacy of microseismicity and how it gives you an immediate picture. If you have the immediacy in terms of monitoring casing failure, because it does rapidly pollute aquifers, and then we would have to mediate for that.
No, I think you're right. I think a catastrophic failure could lead very rapidly to pollution incident and escape of fluids. I think that there is, you know, I mean, ideally there's a need to ensure that there is monitoring in place to regularly check the integrity of the during and to provide early warning of leakage. Clearly, during the process, there are blowout preventers incorporated during the drilling, but also there needs to be, these. I think potentially there is good opportunity for some innovative design to have early warning leakage systems there. And it might be, because of the nature of the fluids, it could be fairly simple by just using something like electrical conductivity to simply measure whether, because they've got high chloride in the produced water and flowback waters, it could be just a simple parameter like that being monitored.
Saving your questions for the closing session, I can tell. Move on now, thank you, Rob. And